Okay, so we're covering mechanical rate now, and this question will pop up in your bell ring. So think about this question right now when we're working through the notes and answer the question tomorrow. So when you think of the word rate, what do you think it means when we apply it to our systems that we've been researching? So what is rate in a mechanical system? What is rate in a fluid system? What is rate in an electrical system? And what is rate in a thermal system? So essentially, rate is just how fast something is moving. So mechanical systems would be how fast those parts are moving or how fast the machine is moving. Fluid system would be how fast the water is moving. Electrical system would be how fast the electricity is moving, which would be your charge, how fast your voltage is moving. And then thermal systems would be how fast your temperature is moving. So that in general is rate. Okay. So I have these videos in here for you guys, and I can attach them to our Google Classroom post. You can watch them. There's a video here as well. So this one would just be in general, what is rate, the overview for rate. So these are our objectives we're going to be covering here. Alright, so rate in mechanical systems, day one. We have day one, day two. So day one is the easier one of the two. So here are the goals if you want to read through them quick. So some equations we're going to be using here. We have, in general, we have velocity equations. We have average velocity, which is just distance over time. And we have acceleration. Okay. And then down here, all this crazy stuff here, that would be angular velocities and angular accelerations. Those are Greek letters. That's omega, that's alpha. That would be in our second day. Okay. These are a little bit more difficult. If you remember radians, that's where we use radians. Okay, so those are our goals for the section. So, in general, what is a rate? So you can kind of read these definitions here to think about rate in different contexts. So, one, amount of charge or payment relative to some basis. A 10-minute phone call at a rate would be cost, or a 10-minute phone call at that rate would cost $5. So maybe the rate would be cost per minutes or something like that. Or cost for now, for 2020, would be cost per gigabyte or cost per megabyte. Okay, those would be our data plans or something like that. So that could be a rate when it's come to money. Number two, a magnitude or frequency relative to a time unit. They traveled at a rate of 55 miles per hour. The rate of change was faster than expected. The dropout rate, something like that. Okay, so like interstate would be 75 miles per hour. So that would be a mileage when you're driving, or a rate when you're driving. Okay, dropout rate. Kind of think of statistics, maybe high school students or people dropping out of a race or something like that. Or college students even. The rate of change was faster than expected, so that would just be rate in any kind of system. Okay, we're going to kind of bounce down to the bottom. So rate is a magnitude or frequency relative to a time unit. Okay, so it has to be comparative. There have to be two things compared. Generally, when in mechanical systems, we have to have that time unit. Okay, so examples would be heart rate, cost per minute. Okay, miles per hour. That's what we're talking about in this section, mechanical rate. We have to have some kind of a time unit. Okay? So, in general, we have to know what motion is. So this is a pretty basic idea, right? But if we think about it, how do we know an object is moving? Okay, so we have this car here, just kind of chilling here, and we have this nice little reference point, or the distance here. How would we know this car is moving or stationary? Well, right now, it's not going anywhere. But say we had different pictures where the car was here, and the car was here, and the car was, so this is here, and the car was here. So different pictures in time where the car was at these different points. And then, since we have some kind of a diagram here, we have car here, car here, car here, car here, we can say that car is moving because it's at different positions at different times. Okay? So the idea here is an object is in motion if its position changes. So you have to have some kind of a diagram to show that the position is changing with the object. Okay? So simplest kind of motion an object can experience is uniform motion in a straight line or linear motion. Okay, so linear, the big idea here, linear motion is the easiest. We're also going to talk about rotational motion. That is a little more complicated, but this one is more applicable because everything does not move in a perfect line, right? If we think about the application of things moving in a circle or rotation, this would be any kind of motor. Any kind of motor or any kind of robotic arm or something like that, gears, this is probably going to be used more often than linear motion, okay, in today's society anyways. So, vector and scalar review. So what are vectors? What do they cover? Vectors have size and direction. Okay, so vectors are quantities that both have size and direction. Okay, so we can read through those, write them down. These are review questions. So what are scalars? Okay, a scalar is just a quantity. Alright, so that would just be your time, distance, temperature, something like that, or time of day, something like that could be a scalar. Vectors both have to have size and direction, and scalars just have size. Okay, so kind of review this here. Vector addition and subtraction. Read this problem. We'll look at the question here. So we have someone that is walking down the sidewalk and they forget their phone. They walk back to the house, grab the phone, and continue on the walk. Then he walks for 100 meters, stops at the end of the block to check a Snapchat. Let's draw a vector diagram of the scenario. Alright, so this is linear motion. Okay, so it's pretty simple. We're just walking forward and backwards. So Steve, first walking 50 meters. Okay, we don't have to really measure this out, kind of just eyeball it. So 50 meters down the sidewalk before we realize we forgot the phone, and then we walk back to the house. So we are here, and then we walk back 50 meters. So that would be a negative 50 meters. Okay, that's positive. Positive 50 meters, negative 50 meters. And then we're back at home. We pick up our phone, and we start walking again. So that is 100 meters. What is his distance? What is his displacement? So we have a couple of topics to talk about here. So distance is usually total amount traveled. Total amount traveled. And displacement, usually given by this, is the distance from the starting point. Okay, so this one is easy. We just calculate how far he went from start to finish, add up everything together. This one we have to remember a little bit more because this is your distance from the starting point. So let's call distance, that's just d, and displacement, that's delta x. Let's calculate the two of them. So distance, I went 50 meters there, 50 meters back, and 100 meters there. Okay, so I went 50, 100, 200. So my total distance traveled is 200 meters. Okay, that one's pretty easy. We just add everything together. So displacement, we have to figure out how far we went from our starting point. So I started here, 50 forward, 50 backwards. So I'm back here again. Okay, and then from here we're 100 meters forward. So where am I from the starting point when I end? Well, these two kind of negate each other, and I am 100 meters out. So my displacement is 100 meters. Okay, so distance is 200, but that would just be total distance I walked, and my displacement is 100 meters. Okay, so here is a pretty basic example of vectors. I have two vectors that are drawn, and I'm doing vector A plus vector B, vector A minus vector B. So draw a diagram and add them together. So vector A, 10 meters plus vector B. So if you forgot how to add or subtract vectors, we do tip to tail. So this is the tip of the first one and tail of the second one. So what's my total distance here? Well, that's just 10 plus 15, so from here to here, that's 25 meters. Now the second one, doing tip to tail again, so that's A, so it's 10 meters, minus B. So that means we're going to take this, and we're doing a negative, so it flips to go that direction. So tip all the way to tail, so it's negative 15 meters. So my answer here would be negative 5 meters. If I were to draw vectors for my answers, these would be my vectors. Because remember, the resultant vector is whatever is left over between the two, or whatever you get when you add the two. So that's my 25 meter vector, and that's my negative 5 meter vector. We're 5 backwards from where we started. Okay? So we kind of talked about this already a little bit. So take a second here, think about the difference between distance and displacement. So if I were to calculate my total distance, that would be the total amount of time that we went on the walk, or the total amount of meters that we took to take the entire walk. Okay? So distance is usually larger than displacement. It can be the same thing, but distance will never be less than displacement. So displacement is the shortest path from beginning to end. Okay, so my displacement would be much less than my distance here. So some definitions, you can have these to write down. Distance in general, how far something travels. Displacement, how far something travels in a given direction. Okay, so displacement is a vector. So what's that mean again? Size and direction. So displacement has both a size and a direction. Or distance is a scalar, so it just tells you how far. So distance just has size. Okay. All right. So moving on, we have an example here. A skier goes from A to B, then C to D. What distance does she travel? What's her displacement at D? Okay. So examples like these pop up quite a bit for distance and displacement, because we have a person going backwards and forwards and backwards and forwards. We try to figure out how far they went for a total distance. So again, we're going to say distance is just d, and displacement is delta x. This is change in distance, or change in position rather, from beginning to end. Okay, so let's look at distance first. So what distance does she travel? So this skier goes from A to B, then B to C, then C to D. So let's write out these different distances that we traveled. And right here is our scale to find the distances. So we went 40, 140, so that's total 180. So my first one is 180 meters. Okay, then my second one here, that's going to be 40 and 100, so 140 meters. And then my third one here, from C to D, I'm going 100 meters. Okay? So to get the distance, we just add total amount traveled, so 180 plus 140 plus 100. Okay, so 180 plus 140, that's 200, 320, so that's 420 meters for my total distance traveled. Now the next one, our displacement, we have to consider direction here. So this is 180 meters forward, 140 meters backwards, and then 100 meters forwards. Now you could just add these together, positive 180 minus 140 plus 100, but it might be a lot easier just to kind of say, where did we go from beginning to end here? How far did we go? 140 and 100. So that is 140 meters for my displacement. Okay, you could do this because that kind of treats them like vectors where we add them. But I think it's a lot easier just to do this where you think from beginning to end. Okay. So the next concept to think about is average speed. All right, so we've just covered motion, how far we're moving, and now we're going to talk about how fast we're getting there. Okay, so average speed. You can read this. The average speed is distance over time. Okay, this is the general formula for average speed. We're going to use this a lot, so I can write that down. So speed or velocity we're talking about here. Velocity is distance over time. Velocity is a little bit different because we have to have that direction with it, but that is comparable. So velocity is difference over time, or distance over time with direction. Velocity has that direction with it, speed does not. Okay, so speed is a scalar, velocity is a vector. So we're going to add a little vector symbol over there. Okay, so units for speed, pretty simple. Distance is measured in meters, time is measured in seconds, so speed is meters per second. If we talk about, if we say velocity, you're going to have a positive or a negative in front of it. Okay? So, why do we care about average speed? So kind of read through this. As the car moves, it often undergoes change in speed. So that would be like if you're driving on the interstate, you don't go 75 miles an hour perfectly all the time. Kind of slow down, speed up. Okay? So during an average trip to school, there are many changes in speed. Rather than the speedometer maintaining a steady reading, the needle constantly moves up and down to reflect the stopping and starting and accelerating and decelerating. So, in an average trip, let's say you're driving to school, you could change your speed 10 to 15 times easy. If you want to become, or if you want to make a nice estimate of what you drove, then you would say average speed. Okay? So the speed limit, say in a residential area, is 25. Speed limit on a highway in town is 35. So you would figure out how long you drove for the 35, how long you drove for the 25, and you can take out and figure out your average speed. Or a nice and easy way to figure out your average speed, just to say your total distance, so how far you traveled over your total time. Just like our equation, right? Speed equals distance over time. That would probably be the easiest way to do it. Okay? It's less complicated is the idea. So velocity, we talked about this a little bit. Velocity here is distance over time, which we saw before, but it's in a given direction. So we need a direction here. So that would be like your positive or negative, forward or backwards, something like that. Okay. So think about this example. If the speed of a skier in the previous slide could be 10 meters per second, the velocity would be, what's the difference between speed and velocity? We'd say 10 meters per second downhill, or maybe 10 meters per second forward. Okay, so these parts to the velocity give that direction, make it a vector. Okay, if we have just 10 meters per second, it's not a vector, but when we include that direction, we now have a vector. Alright, let's try a few example problems. So a runner makes one lap around a 200-meter track in a time of 25 seconds. So let's do this. This will be like an indoor track. Pretty terrible ellipse. 200 meters, time is 25 seconds. Average speed. So what's the runner's average speed? So speed is just distance over time. This is an important equation to have written down somewhere. So speed, our distance we're covering 200 meters, time is 25 seconds. We just divide those two and we get what? 8 meters per second. Okay, so that's the runner's average speed. Now, talking about average speed again, is the person running constantly 8 meters per second the whole time? Probably not. There's probably other racers involved that have to slow down and speed up. Alright, second example. According to the World Disc Federation, on April 8, 2000, Jennifer Griffin threw a frisbee for a distance of 138.56 meters, so let's write that down. To capture the women's record, if the frisbee was thrown horizontally with a speed of 13.0 meters per second, how long did the frisbee remain aloft or in the air? Okay. Well, we're going from, let's say we're covering 138.56 meters before we hit the ground. We have a speed of 13 meters per second. Let's use our equation. Speed equals distance over time. So our speed is 13 meters per second. Our distance is 138.56. And our time, we don't know. So how do we solve something like this? Well, you want to ask yourself, how do I get the time out of the bottom? You have to multiply it out, right? Then we have 13t, okay, because we multiplied that out, equals 138.56. Now we get rid of 13 by dividing it out. And you're going to put that in your calculator, and you get a little bit over 10, okay? 138.56 divided by 13, you get 10.66. So 10.66, and we solve for a time, so 10.66 seconds, okay? So this equation right here, not too terrible, pretty simple equation. We have speed, we have a distance, we have a time, okay? So going on to the next thing here, position time graphs. These are a little bit more difficult. So we have graphs that we can make using motion. Okay, so this is called a position time graph. We have the position on the left here, and we have the time on the bottom here. So the time would be your x-axis, position would be your y-axis. Okay, so we're looking at this graph. We want to kind of analyze it a little bit to figure out how far the person walked. So we can use it to figure out how far the person is, or how fast the person's going, how far they walk at a certain amount of time. But these are the couple specific questions we want to look at. Okay, so how far did the person walk after 6 seconds? So we go to our graph. This is my time, 1, 2, 3, 4, 5, 6. How far did we walk after 6 seconds? Okay, 6 seconds have gone past. I go over to my y-axis. I have gone 30 meters. Okay? Now, what can we say about their speed? If we look at this graph, what can you say about the speed of the person here? Is it changing or is it the same? Okay? Well, after second 1, we went 5 meters. Second 2, we went 10 meters. Second 3, we went 15 meters. Second 4, we went 20 meters. So, what is the rate here? Okay? Their speed is constant. Constant at what rate? Okay? Well, we went 5 in a second, 5 in a second, 5 in a second, 5 in a second. So that means we're at 5 meters per second at that constant rate. How can we figure that out without just going second by second? Because you're not always going to have 1 second, 2 seconds, 3 seconds, 4 seconds, right? Well, the best way to figure that out is with slope, okay? So there are times where we're going to have to figure out the slope of that line to figure out how fast things are going. Okay, so here's a question to think about. What would the graph look like if the person started from the same place but went the opposite direction? Okay, so that means we're still starting from here, but we're going the opposite direction. So that means we would go 5 meters back. Okay, so it'd be something like that. And if we were to draw a line, it would look like that. So it would look the same, like the slope would be the same, but it would be going negative. Okay, so that's the point here. So the person would be going a negative direction. Okay, because if we're talking speed, or actually if we're talking velocity, displacement, stuff like that, position versus time graphs, we can have positive and negative position. Now, will time ever be negative? Probably not. Now, you could say that time is negative given a reference point, but for our purposes, time will never be negative. Okay, so let's try this example problem. Question 1. Where was Juanita at time t equals 0.5 hours? So Juanita is this line here. I'll get to scroll down a little bit. Okay, so at time t equals 0.5 hours. So see if you can kind of eyeball where the person is at, and then follow along here. So 0.5 hours is here. Where is she? Right there. So how far has she gone? So you kind of have to break this apart in your head so that we were going from 2 to 3. So we're here. So we're maybe at 2.3, 2.4 kilometers. We have to pay attention to our label too. Okay, so we're kilometers. So let's say 2.3 kilometers. Okay, question B here. At what time was the magnitude of Heather's position equal to 2 kilometers? So Heather is this line, and it says at what time was the magnitude equal to 2 kilometers? So we're going to go to 2 kilometers, and then we can figure out the time. So that's right there, and let's see if we can figure this out. So 0.5, 6, 7, 8, so we're probably like 7.5, maybe 7.6. So 0.76 hours. Okay, so that's how we use these graphs. If we have a time, then we can find a distance. If we have a distance, then we can find a time. Okay. So if we have multiple things on a position time graph, it's a little more complicated, but we can find some extra information. Okay. So we can graph multiple things on one, or multiple lines on one graph, and the key point here is when two things intersect. When two lines intersect, that means they're at the same place at the same time. So we have kind of a lot of intersections going on here, so we could say that person A, person B, and person C are all at the same place at the same time, or very close right there. Okay? Down here we have an intersection point there and there. So A and D are at the same place at the same time. And then this one would be C and D at the same place at the same time, which we can use the graph here to describe that. Okay, so let's look at another example here. We have two things, two graphs again, or two lines again on one graph. So the questions we're looking at is, where does Ty pass Luis? Okay, so Ty is the bottom line here. Luis is the top line. So where do they pass? Okay, so right here, they're at the same place at the same time. Okay, so where do they pass? You could draw a line, kind of make this a little bit easier. Okay, maybe that's a straight line. It's not perfectly straight, but it's close. So, okay, so we could say Ty passes Luis at 40 meters. Okay, if we wanted to answer this question, when, we could use another line. Okay, if you didn't have a line tool like this, then a ruler is amazing. So that's at 20 seconds. Okay, so 40 meters and 20 seconds. That's when Ty passes Luis. Alright, so what can we say about Ty and Luis's speed? So can we give any information about their speed? So we can move these lines out of the way. What do you say about Ty's speed compared to Luis's speed? Okay, Ty is going to be the faster one because his slope is greater. He's making more change over less time. Luis is going to be the slower of the two. Okay, now they're both moving fairly quick, which I can tell that by the slope of the line. They're both fairly steep. They're almost vertical lines, right? But whichever one is steeper, which would be Ty here, then that is the faster of the two. Okay, so hopefully we followed along. We learned how to cover speed, we learned how to cover distance, displacement, and time, and we learned how to solve for any one of those four. Alright, so we learned also about position time graphs. So your assignment is going to be a worksheet that covers this information. So please work through this if you need to. You can review the video again and look over specific examples, or you can also read the textbook, okay? So let me know if you have any questions. Thank you.